Good morning, students. On continuation of induction motor, in this class we are going to draw equivalent circuit for three-phase induction motor as compared with transformer, and we are going to draw vector diagram of three-phase induction motor, primary side and secondary side. As we discussed previously, the construction of three-phase induction motor, its working principle, and how the parameters of stator and rotor changes based on the slip speed. As we know that this induction motor similar to the transformer. First case, analyze what is the relation, how we are going to draw equivalent circuit similar to our transformer, whether there is any relation of this induction motor and transformer. Yes, so because our induction motor and transformer works based on same principle, that is induction principle, but we have some differences. What are the differences? Whereas transformer is a static machine which can transform energy from one circuit to the another circuit with same frequency without changing frequency, okay, but we can change the voltage and current correspondingly. So this transformer can be used to step up and step down purpose, mainly in our electrical field. It has the it has the primary winding, it has a secondary winding, both are connected, isolated each other electrically but magnetically coupled to each other. And you know that whenever the AC supply is given to the primary winding of the transformer, it establishes its own magnetic field in primary side or primary coil, and this produced magnetic flux in alternating in nature due to the AC supply d phi by dt, and this change in flux links with own conductors, that is primary conductors. Then as per Faraday's laws of electromagnetic induction, it induces an EMF in the primary, and this induced flux or produced flux will linked with the secondary coil which is placed side by it, and it also links the secondary conductors and induces EMF in the secondary. That induced EMF, we can say that mutually induced EMF. As already we have seen that EMF induced in the primary, that is equal E1, that is equal 4.44 flux, frequency and number of turns, and whereas E2 EMF induced in the secondary, that is also 4.44 flux, frequency and N2, because the primary and the secondary windings are wound in a concentrated winding. The number of turns in primary and secondary depend upon our requirement, depend upon our applications. As you know that number of turns in secondary, if less, then we can say there is a step down transformer. If the number of turns is more, that is equal step up transformer. The step up transformers generally used in our power generating stations, whereas the step down transformers can be used at distribution substations. Now, this is a similarity already you have learned in second year level. Here the primary, which is just like our stator winding, and the secondary just like as a rotor winding. The primary, which is given to the supply, here our stator winding is given to the supply, and secondary is connected to the electrical load. Now, here rotor is connected to the mechanical load. Okay, whatever the primary energy is transferred to the secondary through the iron core. In case of our alternator, whatever the power, AC power in stator, is transferred to the rotor through air gap in the form of magnetic field. In secondary of transformer, entirely that is electrical in nature. Energy is the electrical power. So that is given to our electrical loads like ceiling fans, tube lights, etc., etc. Whereas the AC supply is given to the stator winding of our motor. It establishes a magnetic field similar to the transformer, but it is linked with rotor winding. It generates, it produces some energy. That energy in the form of, so some electrical energy in the form of mechanical energy. So due to the mechanical energy, the rotor rotates in one direction. Okay, so this mechanical energy equivalent to the electrical energy which is transferred from stator to rotor. That is motor principle. So we have seen all things. Now for the performance analysis of our induction motor, similar to the transformers, we are going to analyze what are the parameters. What are the parameters of our transformers? The primary winding, it has the resistance value and inductance value, and R0 and X0 components, which is the magnetizing component and working components. Similarly, in secondary also, the secondary winding, it has a secondary resistance and secondary inductance values. Same things here also, but the secondary is a stationary, our secondary is the rotor part. And at the same time, we have seen the parameters, that means what are the secondary values. The primary values are similarly both in transformers and in our motors are similar. Input voltage and input current and everything is frequency, or everything is same in case of stationary part. But whereas the induction motor, before starting its rotation, it is a standstill condition. At that condition, it looks like a secondary transformer is short circuited condition. Once what happened when the motor is at standstill condition, then the frequency of stator is equal to the frequency of rotor. Okay, so same thing. And once rotor starts to rotate, then its frequency changes and its induced voltage value changes, and the parameters, everything is changes. That is based on what factors? That depend upon the slip, percentage of slip. Yes. So these are the some introduction and previous history of both machines. Okay, let us, so these all things based on this idea, so we are going to draw the equivalent circuit of an induction motor. Okay. So let us see in details. Now what is happened? So what we have discussed in this one, we will go step by step. Now this is, dear students, please see it. This is a one transformer. Okay. So I am taking now for phase values. Now what happened? Stator has stator winding, that is equal to here primary winding. Next, this is connected to the secondary winding. Once primary current is I1, secondary current, if load is connected, that becomes to the I2. This is called V2 and this is the V1. And here the frequency is a F. Here frequency also F, same frequency. Here is a N1, here is a N2. Okay. Now the primary, when supply is given to the AC supply is given to the primary, it establishes its magnetic field. The field will flows through the ferromagnetic core material, links in stator N1 conductors and N2 conductors. So based on N1 E1 EMF induced in the conductors of primary, so we can say this self-induced EMF, that is depend upon the 4.44 and maximum flux and F into N1, and induced EMF in this one also E2, that is equal E2. Here is the E1 self-induced EMF. This is a mutual induced. What is the E2? E2 is equal to, we can write it 4.445 F and N2. Here is a similar. So that depend upon the only number of turns. Okay. Now this is the in case of our transformer. Now, so what we have seen here, the primary frequency and secondary frequency is same, and whereas in our induction motor, so for example we take the induction motor now. So this is the primary, that is equal to stator, and next this is equal to rotor. Okay. So what is happen here? The primary act as a state, this stator act as stator, and this is the rotor. Okay. The stator has, similar to the primary winding of transformer, and secondary act as a secondary of transformer. Rotor act as a secondary of this one, and this stator act as a primary of this one. Now what is happen when supply is given to this motor, three-phase supply, and it produces the magnetic field. Okay, that produces a magnetic field, and that magnetic field produced is rotating in air gap, whereas this produce a flux so flowing in a core, the closed path, because all magnetic fields are closed path, but whereas the closed path always is the rotating at a speed of ns. It is rotating in a synchronous speed. It is a dynamic, it is static. What is the reason? Because in stator winding, the winding is a distributed winding. Winding is a distributed. A stator or rotor also distributed, whereas this is a winding is a concentrated. So here is a concentrated winding and concentrated winding, and whereas this is a distributed winding, this is also distributed winding. So that's why, so this rotating magnetic field links with the stator conductors as well as the rotor conductors. Similar to the transformer, it is also induced EMF, that is equal, the stator induced EMF is equal in stator conductors as per self inductance, that is equal 4.44 flux frequency N1, number of conductors this one, and Kw1, that is a winding factor, that is a distribution factor and pitch factors. Okay, now in EMF induced in the rotor is equal to, so 4.445 F, here N2 and Kw2. Okay, here rotor at standstill condition, this is for example, this is a AR is equal to FR, you can say it is the FR, where, so this is the voltage. Now what is happened here, this is the induction motor, this is the transformer, this is the induction motor. Transformer values are this much and induction motor values are this much. As we know that in transformer, so transformation ratio K value, you can write it. What is the K value? As you know that K value is equal to N2 by N1 and E2 by E1 and V2 by V1 and I1 by I2. Simple, this is known as a transformation ratio of transformer. Now similarly we can write it, this equation here, what is happened, En, that is equal ER by, and you can the E stator, rotor in, that is we can say that this value, divide is equal to, we can write it Kw2 by Kw1 into N rotor by N stator, sorry, this value. Okay, this is known as the transformation ratio, we can say this is equal K in our induction motor. Okay, dear students, so what is the transformation K? What is the need of the K? K is required to transform the inductive values, ohmic values from primary side to secondary side. Here also we require this is transformation ratio. Okay, after knowing this one, now I want to draw the equivalent circuit diagram. K we know. At the same time, so you should know, so this is a winding, this is a winding. Okay, so what is the winding? This is a winding, and this is also winding. A stator also winding and rotor also winding. Now what are the parameters? Now if you are seeing the parameters of transformer, so what has happened? Transformer has the primary winding, this is the primary resistance and this is the primary inductance, and we know that that is equal equivalent components R0, X0 of this one and connected to here. Okay, now this is connected to primary equivalent circuit. Now we are going to connect, this is also connected, this one. So what is this values? So what is this value? This is equal to R1, this is equal to X1, R0, X0, okay, and these are the values. Now we are applied voltage is equal to V1, current is flowing is the I1, and current flowing through this one is the I0. Okay, now in secondary side, so what is the EMF induced? This V1, and here voltage induced in this case is equal to E1. Okay, now coming to this one, the EMF induced in the secondary is equal to E2, and this is equal to R2, this is equal to X2, the secondary. In This is called, we can do the V2. These are the equivalent circuit diagram of a transformer for phase values. Okay, so these are the diagram. Similarly, we are going to draw this diagram also. So in our induction motor diagram. So induction motor diagram also we can write it similar way. So we can change the color. Now you can see. Now what is happened? So because here what is happened? This also stator has a winding and rotor also winding. Okay, then we can write it here equivalent. Okay, you can see this can the stator having the stator winding and connected the three-phase supply, and rotor has a rotor winding. Okay, based on this one, stator winding, I can write it. It is also winding. It has some resistance, some inductance. It is also some magnetizing components, and this is also this one, and they are connected here. It is connected to our primary side. Okay, so similarly, it's rotor side. We are going to connect it. This is equal to resistance, inductance connected because short circuited under running condition. Okay, so what is these values? Now these values are the R1, X1, R0, X0. Okay, induced voltage similar to this E1. Okay, this voltage is equal to V1. Okay, current is equal to I1. Similar to this one. You can see similar values. Okay. Now here this is the R2, X2 shorted here, and here induced voltage is equal to E2. Okay, so V2 is equal to here 0. This is the equivalent circuit diagram of our induction motor, stator and rotor. Now the current is equal to I0. This current is called I1. This current is called I2 current. Okay, now coming to this can be written as, so we can written as, this can be written as this resistance, inductance, and we connected some this value, this inductance value, and connected here. Now we can simply write the just like transformer. Okay, this is equal to this one and shorter. Okay, this is called R1, this is called X1, R0, X0, and this is equal to E1, this is equal to, you can say the ER rotor values, this is called R2, X2. Okay, equivalent values. Now this is equal to V1 and frequency F. Okay, I0. So reduce this one. Now actually this is at standstill condition. So standstill condition, rotor is shorted and it works as a secondary of the transformer is short circuited condition. At that condition, this is the secondary winding parameters, the primary winding parameters. It is a magnetizing current working components, as you know that. Now actually this rotor values at slip condition. This is the standstill condition. S is equal 0. Sorry, S is equal 1 at standstill condition. Now slip in between, S between 1 to 0, in between slip speed. what are the parameters in rotor circuit? We know that rotor parameters are changes based on the slip. Okay, now what are the parameters now? So same thing, I can write it under some speed, yet slip speed at S. Then rather primary side is the same. Okay, whatever the values are, I can write it this one. Okay, so I can write it this one. So what is happened? This is equal, I can write it, this one I can write it and shorted. This is equal EMF induced, that is equal to S into E2. This is equal to R2. This is equal to S into X2. This is equal to I2. Why? Because we know that under S slip condition, the frequency of rotor is equal to slip times of frequency of standstill condition. Okay, now the ER, rotor EMF induced in the rotor conductors, is equal to S times of EMF induced on standstill condition. So based on these factors, this value changes. Now how this value changed? Now as we know that here R resistance independent of frequency, So that means R1, R2 is equal to R2 at S speed also. So because it does not depend on the R is equal to rho L by A, that is dependent on the length of the conductor, area of the cross section and the property of the resistivity of the material. So does not depend on the frequency. So whatever the R2, that is under running condition, under standstill condition, that value is the same. Okay, that is clear. Now so here what is the value changes? This value changed and this value changed. So this value, so we know this is completed. Now why it is changed? Now we can see here, because here what is happened? So inductance value, X value is equal to omega L, that is dependent upon the 2 phi FL. So frequency, that is the inductive reactance depend upon the frequency. The frequency changed from frequency F1 to FR. So what is the FR? FR is equal to S times of standstill condition F1. That's why we written instead of 2 phi S into FL. So that's why it changed to this value. Okay, S times it changed this value. And similarly, Z also changes. What is a Z? Z is equal to R plus J of XL. Now R, can write it R2 plus this XL. What is the value? Changed this value. So I can write it J into S into XL. So Z also changes. So that means if frequency changed under slip speed, then R does not change, the XL becomes to SXL and ZL becomes to SZ. Okay, so that value also change, S times of Z value changes. So you remember these things. Okay, so after these values, what are the value changed? So now I am going to write it this equation. So what is this this equation? I can write it this equation. So what is the current now? So I can write it this equation, that is equal to, here this is source, this is the source, that is equal ER. Now it is going to the resistance, then it is going to the inductance, this value. So R2 S X2 and this is equal ER is equal to, you can write S into E2, this value. Now I want to know the current. So I can write it current is equal to, what is the current? I is equal to voltage. What is the voltage? Voltage by impedance. Okay, so what is the impedance here? Voltage. What is the voltage? This is the voltage. So I can write E2 SE2 divided by, what is the value? R2 whole square plus SX2 whole square under root. This is the current in the rotor. Okay, now by divide numerator and denominator with S. Okay, so 1 by S you divide numerator and denominator. Yes, you can write the S. Okay, or either take out the S, then you can write it S E2 divided by, so I can write it R2 by S whole square plus X whole square under root into S. Just I taken out this S and this S get cancelled. I am going to U2 by root of R2 by S whole square plus X2 whole square. This is a simple equation. Okay, this is a simple equation. So I can write these values instead of these values, and I can, the new equation I can write it. What is that one? So from this one, so I can write it, this equation, this is a drawing. Okay, so this can write it. So this can I write it. Write it. So this is a direct, I can write it the E2, I can write it, this is a R2 by S, this I can write the X2, this is current the I2. Okay, so this is the secondary equivalent circuit diagram. Now what can write? I instead of I want to this, because what is happen? We know that in rotor the power is, whatever the power, rotor power, input power is equal to P2, and it is given the rotor take the P2 and it will gives the two powers. One is the PM, another is the P copper. Okay, that is the electrical energy as well as the mechanical energy, rotor. So here is the total electrical energy, there is no mechanical equivalent values. That's why I want to convert this circuit into the mechanical equivalent of electrical circuit. So as you know that whatever the P2, so the P2 is equal to power input to the rotor is equal to sum of the power, the copper losses, and sum of the total mechanical power developed in the rotor. We know that, so here copper losses, P copper losses is equal to S times of P2. So already we know these relations. Now the copper losses can be written in the form of current and resistance. So I can write it I square I2, that is called I2 square R2. I can write it this one, and this is called S, this is equal P2. I want the P2, then I can write it P2 is equal to, I can write it I2 whole square R2 by this S, okay, S value. So what is the P2? So P2 power input to the rotor, I can write it copper losses by slip. Same thing I am going to substitute here. Here, substitute here. Okay, so here. Now you can write it. What is the P2? So I can write it P2 is equal to, so I2 R2 by S, okay, is equal to, what is the copper losses? Simply copper losses I2 whole square R2 plus PM. What is the PM? So I can write it PM also. Here the PM is equal to 1 minus S into P2. So we know that the equations already, how the power transfer, this known. So based on this one, so I know this one, I know this one, so I can write it. What is the P2? So that is equal, instead of Im I can 1 minus S, okay. So that is equal this value into P2. What is the P2? P2 is equal this value, okay. That is equal I2 square R2 by S, okay. These are the equivalent circuit here. Now what is happened? The current is taken out. So what is the current here? So I2 square taken out. Then I am going to get the values in the only resistance value. Here R2 by S equal to, so here R2 plus 1 minus S by S into R2. Okay, these are the equation we finally arrived. That is equal R2 by S. Can I write it in the form of R2 plus R2 in some terms? So this value, whatever this value, now here this value I can write it this equation. What is the equation? I can write this equation. Okay, then the circuit becomes, this simple circuit, it becomes, what is the value? Now once again I can write it, okay. So I can write it, so I can write it, so whatever the, this is equal to, this is equal to, it's a E2 R2 by S and X2 this value, okay. I can write it this one R2S, I can write it. Similarly this is equal to, then I can, what is the value? Here I am going to get R2 by S, this R2 by S, I can write R2 in terms of this value, okay. Some resistance here R2, I can write it R2, okay. At the same time I can write it, okay, it's two values, you can see this terms and the term, so that you can write it R2 into 1 minus S by S, okay. Anyway, this is the inductance value X2, so I can write it these values, okay. Now the current is same I2, so this can be simplified, this can be written once again. So this is equal to resistance, inductance, resistance. This is the variable resistance. So this is R2, X2, E2, and we can write it, this is equal to R2 into 1 minus S by S. So we can say this value is nothing but RL, load resistance, okay. So this is a rotor values. What is the stator value? So once again you write it this value in stator. Where is the original figure? This is our original figure, okay. So this can be written in the form, original figure is this one. Now you can write it the equivalent circuit diagram. Now stator is same. What is the stator? Stator is the resistance, inductance, parameters, these values, and this is the value, okay. Now this is nothing but, you can write it this one. Now secondary I can write it resistance, inductance. Now here is the load, okay, connected here. This is this one. So R2, X2, E2, this is the RL, okay. So this is X1, sorry, R1, X1, R0, X0, okay. So these are the values. Now what is the current values? Now current is equal to I1, current is the I0, the current is the I mu, IW working component, this is called I mu, and this is called as I1, Okay, so you can write the I2 dash, this can write the I2 dash current. Similarly, this is the I2 current. These are the equivalent circuit diagram of our induction motor. Now, whatever these values refer to the primary side. So once what are the values in the secondary side to the primary side, so we have to divide it by K square, transformation ratio. Okay, as you know that, just you simplify this one. Okay, so what is happened, this is equal, now so this becomes to the equation. So this is resistance, inductance, and this one, and now it becomes to the resistance, inductance, and equivalent this value connected to the here. Okay, so this is called RL, this is called R2 dash, this is called X2 dash, this is called dash. Okay, refer to the primary side. This is equal to X0, this is equal to R0. Okay, this is equal to R1, this is equal to X1, and this is equal to V1. Okay, same thing. What is this R2 dash, R1 dash, these values? So this equivalent resistance refer to the primary side. Then we can write it these equations. So R2 dash is equal to R2 by K square. Okay, so what is the K? We have seen E2 by E1, N2 by N1, that's value. Then X2 dash is equal to, that is equal to X2 by K square. Okay, so here RL also, so RL dash, R2 dash, RL dash is equal to, so R2 by, okay, K square into 1 minus S by S values. Okay, once we know these values, and whatever this value, so this value, so I am going to move this direction, because I am going to R1, R2, I am going to write it. Then, so this further equation, it becomes, now you can see, so I am going to write it further this equation now. Okay, no problem. So you can write it, this is equal to, I can write it, this is equal to resistance, this is equal to inductance connected to this one. Okay, now it is connected to the some resistance, some inductance. Now it is connected this one, it is connected to the this one. This is R L dash. This is known as the R naught 1, X naught 1. Okay, X0 and R0. So this is the I0 current. So what is the R naught 1? Now we know that R naught 1 equivalent resistance referred to the primary is equal to R1 plus R2 dash, that can be R1 plus R2 by K square. Okay, that is equal to this value. Now similarly X01 also we can write it X1 plus X2 by K square. Okay, so this is the values, and these two values I can write it Z01, I can write it Z01, that is equal to R01 plus J of X01. So this equivalent value. So finally I am going to get, this is our induction motor equivalent circuit diagram. This is a equivalent circuit diagram. This is we derived. So dear students, so these are the equivalent circuit diagram of induction motor referred to the primary side. Okay, I think you got it now. So what are the values here? I am going to write it. Same values you are going to place. So this is equal to V1, frequency the F, this is equal I1, this is equal to I0, this is equal I working component, I mu, and this is equal to, so current is the I1, so equivalent, this is equal to load current. Okay, these are the equivalent circuit diagram of induction motor. Okay, so now after getting this one, so I am going to write it one diagram that is equal to vector diagram. Okay, so based on this one I am going to write the vector diagram. Okay, so now I am going to write the vector diagram. So vector diagram, vector diagram of induction motor. For phase I am going to write it. Okay, now, so before that one, just you remember what is that. So we have seen here is the this one, okay. Now this is a okay. So now for the simple understanding purpose, come to the basic circuit. Okay, comes the basic. What is this one? This is equal to V1, this is equal to R1, this is equal to X1. Okay, the current is equal to I1. What is the current here? I0. What is the current here? Equivalent I2 dash. This is equal I2 current. This is equal R2. This is equal to X2. This is equal to E2. Okay, so E2. Now this is equal to R0. This is equal to X0. The current is flowing is the I working. The current is flowing is the I mu. Okay, so this is a basic circuit. From the basic circuit we are going to draw the vector diagram. Okay, everything is simple. Now here induced EMF, what is this one? Here induced EMF is equal here E1. So now draw the, based on this one I am going to draw the vector diagram. Now you can take the vector diagram. So you take it one, okay, take the black, take the black. You take the one black graph and you take it this direction. Okay, now you take this is equal to 5 and you take the voltage the vertical side. Now based on this one, now you try the no load current. So I am going to write the these values, this and this values. Okay, so that is the I0 current. I am going to write it. So I can take the voltage. So this side, so this side is I have taken the voltage V, and here also voltage induced, and this is equal to primary side and the secondary side, both are this direction only. This is equal to whatever the voltage induced, voltage is equal to here only. Okay, so now I can write it, that is equal to E1 and this is equal to, this is equal to E2. Now, so based on the no load current, I can write it. No load current is this much I0. Okay, so based on this one, So this is the I0. I0 is going to the IW and I mu. Now I can write it. So here the current is the vectors, vertical component, horizontal component. I can write this is called IW working component. I can write it, this is the I mu. Okay. Now I0 will come. Now what is happened? This is the E2. So this is the E2. You can write it. This is the E2. So opposite to the V, and this is the current I2, because due to the inductance, so I2 always lagged. So E2 in this direction, then I2 will flows in different way. So you can write it I2 value. Now this is the E2, and the secondary side, if you are going to draw the E2, so for example, this is the current I2, some lagged by some angle phi 2. So that is equal to here E2 and I2 is lagged by some angle of phi 2 in secondary. Okay, same thing as written here. Now here I am going to I2 dash, so I am going to the right in this direction. This is equal to I2 dash, 180 degrees apart. Now sum of these two values I am going to write it. Okay. Now what is this value? Sum of these values. So I can write it. So this value and this value, I am going to get the some value of the current. I can write it, that is equal I1. So here vector sum of I2 dash and I0 dash, I am going to the I1 current. Same is represented here also. Okay, so this is current I1 is lagged by voltage by some angle. Okay, that is equal. Now here this one. Now based on this one, now what is happened here? E1 voltage. Now this is a E1 voltage. So what is the here V? The V1 is equal to this drop plus this drop. This is equal to I1 R1 plus I1 X1 plus this is equal, what is this one? This is equal E1 induced voltage here. Okay, E1 plus this voltage, we are going to this one. So I can write it, this is equal V1 and E1. What is the E1? E1 is this direction. So you write it E1 some direction. So we are going to that this is a E1. Okay, that is equal E1. Okay, now we are going to E1. Sorry. Now we can take this is, you take outside first, you take that, this is called, what is that one? E1. Okay, this is E1, or you can take it okay, you take it this one. Okay, now you can, this also you can remove it. Now you write the values. Now you take the another value. Now so this is whatever the E1 180 degrees shift to the this direction 180. This is equal to E1 minus E1. So 180 degrees this one. Now here what is the primary? So dear students, this is equal to R1 X1 and this is equal to E1. This is equal to, we are going to V1. This is equal to E1 induced EMF voltage. This is equal to R1 and X1 current is equal to I1. Okay, same current is flowing. This I am going to write it. So this E1 I can write it this direction up to this direction. Now what is the current here flowing? Same in phase. What is the current direction of I1? This direction. So this direction. So similarly write it this one. So I1 R1 current. And this X1, it is a 90 degrees perpendicular here. So this is a I1 X1. Now what is the value? So this is R, this is a X, we are going to this one. So Z or Z. Okay, so this is called Z, we are going to get it. Now I1 into Z1. So we are going to this value. Now what is this value? So what is the value? Now this E1, so just you write it correctly. Okay, what is this one? You written this one and you are going to come here this direction. Okay, now so what is the E1? This voltage I can write it I1 Z1, I1 Z1 plus E1. I am going to the, so I can write it V1 is equal to vector sum of, so what is the value? E1 plus I1 Z1. Okay, so this value represented by, so I am going to here that value, I can write it another color, dark color, I take it. So the here from this one I am going to write it this equation. So that is equal V1. Okay, so what is the value here? So here, so up to this is equal to this value, and up to this value is equal to I1 Z1 this value, and I am going to this value. Okay, so that means here this is equal to E1 minus E1, and this is equal to I1 Z1, and I am going to get this is equal to V1. Okay, so these are the, I am going to get this angle, this primary side. Okay, and coming to the secondary side. What the secondary side? So here you know that this diagram, this one. So this is a I2, R2, X2, this is equal to E2. So E2 is this much. Now I1 R2, I1 is current, that is called, here current is the, what is the current? I2 current, I2 R2. So that current is in phase with the direction of this I2. So here going to write it, this is the current I2 R2 in phase with the current. Now this is perpendicular to the 90 degrees. Here you can write I2 X2. So that means here I can write it, so E2 is equal to, so I2 into R plus I2 into J of X2. Okay, this is the equation I written here. You can see here. So what is this one? So here from this one to here is the I1 R1, and this is perpendicular, this is equal to I2 R2, this is equal, what is the value of this one? So this value is equal to, I can write it I2 R2. Okay, this I2, this is equal to X2, then this is equal, I can write it, that is equal to E2. Okay, so this is the angle is the phi 2. So this circuit value is written, this one, this is nothing but this one. Okay, now the primary, this one, and this value is written this value. So this is a one vector diagram. Okay, dear students, you can practice it. It's a very easy to draw the vector diagram. Okay, so once again I am writing this concept. First you take the one diagram here, and this is the I0 current, and this is the I2 current, the reversed, this is the I2 dash, a resultant of this current, and this current I am going to that the I1 current, primary current, and here the voltage induced is the E1, and same voltage induced in this is equal to, this is equal to E2 voltage. Okay, now E1 I can write it this direction, because here primary side, so I am going to get this one, so R1 X1 E1 and this is equal V1. The current is flowing I1. So I1, this I1 and R1, I1 is this direction, then you write it this equation. So here first of all you take the E1, so write the E1 is equal, you take the reverse, this is called minus E1. After this is the, this is equal, you can write it E1, okay, minus E1. Now after E1 plus this values, so here this value I want to know. What is one? I1 R1. So what is the current direction? This angle. So you write it this angle. Okay, this I1 R1. Now this value, then perpendicular. I1 X1. Then combine this two. This is equal I1 Z1. Okay. Now they are going to get it. This is some point. Now what is that one? This plus this one. So we can write this value is equal I1 Z1. So here V1 is equal to E1 plus I1 Z1. So here that is called E1 plus I1 Z1. This is I1 Z1. That is called V1. So I can write it V1 in another form. So from this one I am going to write join these two lines. So this is equal V1 voltage. Okay, so V1 voltage we easily calculated if you know the E1 and these values. This is the diagram. This is the primary side. Now coming to the secondary side. What is the secondary side? Here E2 is equal this one and this one shorted. So R2 X2 current is equal I2. Okay, so that is equal, I am going to write it. So here I2 R2. So this is already the current is this direction. The current is I2 R2. Can write it I2 R2 is equal this direction. So write it I2 R2 and J X is the 90 degrees. So this is equal I2 X2. Now this is equal E2. So this is the secondary value. So this equal to this value and this equal to this value. This is known as the vector diagram. Vector diagram of induction motor for phase values. Okay, so dear students, it's a very easy, but you have to just practice 1 or 2 times. Let us summarize. So how we are drawn equivalent circuit diagram of induction motor and how we are drawn the vector diagram of induction motor. Okay, so let us see. So here we have already seen what is the we compared with the transformer. Okay, so here the transformer is given. First we have seen the transformer equivalent values and induction motor values we compared. So that means, so we assumed as a induction motor is similar to the transformer, but it is has concentrating winding in transformer and distributed winding in induction motor. So based on this one we calculated what is the EMF induced in primary side and secondary side here. So from that one we calculated the K values, transformation values, and based on the transformer values we calculated what is the inductance of both sides. Okay, so based on this one I written the stator side equivalent circuit diagram and rotor side equivalent circuit diagram here normally. And here the rotor circuit further analyzed into the equivalent electrical equivalent of mechanical load. That's purpose this circuit is transformed into this way. Okay, so it is next, it is going to this direction, and finally we are going to this into different shapes. Okay, so based on the some calculations we have done, so this is a finally, so we are going to get it this is the final rotor equivalent values. Okay, this one, I think this is the final rotor equivalent. This is the electrical and this is the mechanical equivalent of electrical circuits, and combine this one. So we are going to get it the final equivalent circuit of induction motor. Where is that one? We can see we all are the simple manipulations. These are the final equivalent circuit diagram, and this is referred to the primary side. So we are going to get it, and after removing this one, the shunt towards this one, so we are got it the final equivalent circuit diagram induction motor in for phase values. Similarly, B phase and Y phase also we can write it. Okay, this is the equivalent circuit diagram, and at the same time, so based on the basic circuit, so that equivalent circuit, so we have also drawn the vector diagram. Okay, so vector diagram also we have drawn based on this one. Once again, vector diagram taken, and the primary side or winding with R phase, Y phase, and this is a shunt working component and magnetizing component written, and this frame from this one we drawn and vector form. So this is the vector form. So how we have taken this is the phi, and we taken the E1 and E2 in opposite direction as per the Lenz's law, and based on the current I0, no load current, and I2 dash reverse to the I1 dash. So we are going to draw the vector diagram. So already this is the vector diagram you have drawn. Okay, it's a very simple, just you practice it. Okay, thank you dear students. So I think I have this also explained in PPTs, but I am not satisfied so much. That's why I have made another class for easy to understand each and every student. Even then, if anyone have any query, please ask me in the next class. Thank you for listening my class.